Welcome back. I'm Professor Xiao Ma. In this video, I will demonstrate and explain a specific hands-on problem. This problem is likely in your homework. But keep in mind that for demonstration, I will use example datasets about predicting credit card customer default outcome. When you do your homework, the dataset is different. Make sure you adapt the codes for the homework. Now let's get started. In this particular demonstration, I will actually use fewer packages than the previous recent demonstration about multi-layer perceptron model. Notice I use a random state 30, numpy random seed 30. I moved the useful function to the top because I will not break down for loop processes. We will put the for loop process inside one cell. I will use these two utility custom functions. One is for calculating the sigmoid activation. The other is to calculate forward propagation in one step. I use 4 dataset files for this demonstration. The dataset has already been splitted into train and test sets, and the dataset has already been pre-processed and separated the target from the input variables. So 2 data files for the train set, 2 data files for the test set. Within each, 1 data file for the Y data only, the other data file for the X data only. Therefore, there is no ID column. Read in the Y data and X data. Do some sanity check in terms of dimensions. Print the first 5 rows of Y data for the train and test set. Observe that for the train set, only the row with index 3 has value 1. Other values are all 0. For the test set, the target variable all have label 0 for the first 5 rows. This is mostly because customer default rate is only 20%, so the majority of the customers did not default. Print the information of the X variables using the train set. These information should be mostly similar between the train and test set for the input data. Print the descriptive statistics of the input data set for the train and test. They will mostly be similar. In printing these descriptive statistics, in order to show more columns, I converted the values to NumPy first. The table will look more compact after stripping away the metadata, including the column headers. Recall from the previous video about multi-layer perceptron model, in calculating the model performance, such as accuracy, you still need a flag variable format of the target variable. Here, you do not have that. You only have the one-hot encoded Y data, which has 2 columns, one for the label of 0 and the other for the label of 1. Here I show an alternative method of getting the flag variable for the target besides the method that was demonstrated in the previous video. Here I will use the one-hot encoded format of the Y data to get the flag variable for the target. I use NumPy argmax. This works because in each row of the Y data, the label of the value that is greater inside that row will be flagged. Finally, before modeling, I will convert both the Y data and X data, including the train and test set, in total 4 data frames, convert them into NumPy array, which is similar to matrix. Let me first explain to you at a conceptual level what's the difference of the implementation process between the whole training set gradient descent and mini-batch gradient descent. On this slide, I have put them side by side. I will highlight what is the same and what are the differences so that you can see clearly on a conceptual level how you can go about modifying the processes to add mini-batch gradient descent. As you know, in the whole training set gradient descent, right after you have completed the initialization step, you can start the for loop for the epochs. This is the only for loop that will be implemented in the whole training set gradient descent. In comparison, there will be 2 for loops in the mini-batch gradient descent. There will still be a for loop for the epochs. I will call this the outer loop of the mini-batch gradient descent. The process are more or less the same between the two types of gradient descent, so I put them side by side and they look very similar. The difference with the mini-batch gradient descent is there's something that comes before that, before you even go into the outer loop, which is random number generator object. You need to define a new random number generator to be used for specifically shuffling the indices. I'll talk about that shortly. Now, for the whole training set gradient descent, in each for loop of an epoch, you simply do the forward prop and the backward prop or back prop. After doing the back prop, you proceed to calculate the performances and save the performance, including the cost value and accuracy value of this epoch. Here comes the difference in the mini-batch gradient descent. Before you even go to the forward prop, you have a few new steps. First, you need to create a temporary index array, and you will use that index array to randomly shuffle the orders of the training set that you will extract randomly in each epoch. And then comes another for loop, which I will call it the inner loop. The inner loop is added specifically to do mini-batch gradient descent. So here is the way to think about it. Within each outer loop, you will finish training using the entire dataset. Instead of using the dataset in one step, you will cut the dataset into many mini batches, and every time you will use a subset which is called a batch or a mini batch. You will only use a mini batch to conduct one gradient descent process and then move on to the next mini batch until you have exhausted all the data points in the training set. So this is what the inner loop does. And it's clear that in the inner loop, you will perform forward prop and backward prop. But wait a second, before you can even start the forward prop and backward prop, there's an additional step that you need to do, which is you need to construct a way to subset the randomly shuffled indices in order to extract a mini batch dataset from the original training dataset. This is by using the way you construct the indices for the mini batch in the inner loop. This will become more clear when we look at the codes. Just keep in mind that in the inner loop, you will need to revise the way you use the X and Y data, the training data. Instead of using X and Y, the whole set, you will need to use the indices and slicing notation to slice only the portion of the training dataset that is corresponding to the specific mini batch. After implementing those changes, forward prop and backward prop will proceed fairly similarly. And after you have looped through all the mini batches of the current epoch, you will exit the inner loop and go back to the outer loop. It's in the outer loop you will calculate the model cost and performances such as accuracy and save those values to the list. So let me remind you, calculating cost and model accuracy is in the same level of loop, which is the outer loop. In the whole training set gradient descent, the outer loop is the only one loop. So in a way, the save performance step is quite similar as well, after all those differences that has been implemented before this point. So this concludes the differences and also similarities between gradient descent based on the whole training set versus the mini batch gradient descent. Now let's look at the codes. Recall that previously we added L2 regularization. Here, I'm going to demonstrate how to add mini-batch gradient descent on top of that. The Python implementation here will implement the conceptual changes of the steps that are talked about in the slides. And here is just an overview. Before we modify the codes in the main implementation, we need to slightly modify the codes that we initialize the variables. Here, the only thing that needs to be added is the mini-batch size variable. For this demonstration, I'm using 32, which is 2 to the power of 5. The choice of exponent 5 is quite common for a dataset that is not super large. Everything else here remains the same. Now we begin to modify the main codes. The first thing you will need is a new random number generator. Note that this random number generator is slightly different from the random number generator that we used earlier for drawing random weight matrices. But for this new random number generator, I use the same random state as the seed, which is defined on the top. Then we start to modify the codes in the outer loop. Inside the outer loop, the first thing you will need is to redefine the indices based on the number of cases in the training set. N here is assigned the value, which is number of rows in the current training set. We get the indices, which is natural number sequences beginning from 0 that has the length of n. And then we use the random number generator object to shuffle the indices inside. So observe this. For every epoch, we redefine the indices as a starting point, which will be the same every time we begin a new epoch, but then we shuffle. Because of the random number generator, in every epoch, when you shuffle, the same indices will be different. So in every epoch, the shuffled indices will be different. This will almost guarantee the random gradient descent process is different for every epoch. After the indices are shuffled, you are ready to begin the inner loop. This would be the most significant difference. Let's take a look at these. The main changes are here. Keep in mind that everything here is the inner loop. Inside the inner loop, the training set is simply the mini batch dataset, which is a small portion of the original training set. Be very clear on this, otherwise you might be confused at why we're doing these in terms of the index start position. Because we will only use a small portion of the dataset that has the size of mini batch size, we will leverage the shuffled indices to select only the corresponding portion of the training set, which has the size of the mini batch size. So the beginning index of the current mini batch iteration begins with a proper setup of the range indexer for the starting index. Now spend some time to carefully understand how this process goes. It basically leverages indexes about the indices that you created. The index positions here is created to slice the indices that you created. This is critical. If you understand this part, I don't foresee much more challenges that you will have in understanding the complete process of modifying the codes for mini-batch gradient descent. So with a proper setup of the beginning index, you only need to hop over the step of mini-batch size for every mini-batch dataset, right? Hopping over the same step for the beginning index. And in every iteration of the inner loop, you use that new beginning index for that iteration and simply slice the sides of that index. Simply slice the sides of the indices that is equal to mini-batch size. This slicing notation will slice out the length of the indices, which is equal to mini-batch. Why? Because when you subtract this number from this number, the difference is mini-batch size. You can guarantee yourself that the length of the indices portion for this particular batch is the same as the mini-batch size. Once you have correctly obtained the slice of indices for this batch, you simply use that to slice the portion of the training set for this particular iteration of the mini-batch gradient descent. Then after this point, you only have to update the training set, including the X input set and the Y target set using this new slice of indices. So if you compare the codes in forward loop and backward loop from here with those codes previously with L2 regularization, the only difference you will see is the addition of the slices notation for the data, including X data, Y data, and down below when calculating the gradient of the hidden loop, you need to slice the X data set again. With this change, you're all set for the forward prop and back prop. The only other thing to note would be proper indentation, because you have now an inner loop to implement the mini-batch gradient descent. Although the process of calculating the cost and accuracy remains the same, you want to make sure that you do these outside the inner loop, but inside the outer loop. So this comment is just to remind you that now we have exited the inner loop. The indentation level is the same as the outer loop, but not the inner loop. Within the outer loop, you can safely calculate the costs, save the cost to the list, calculate accuracy, and save the accuracy to the list. Everything else remains the same. Now let's run this. It took about 12 seconds to finish the training. Because of the mini-batch inner loop, the process is a little bit longer than gradient descent on the entire training set. The training time was 3 seconds, now it became 12 seconds. You may ask, what's the point of using mini-batch gradient descent when it takes more time to train? Well, the truth is that we're using quite a small data set when it comes to data science projects, so the advantages may be reversed. The real advantage of mini-batch gradient descent comes when you are dealing with a much more complex and much bigger data set. With that size of the data set, I'm talking about millions of rows and hundreds of columns. With that size of a data set, gradient descent on the whole set is simply not possible. It will freeze the machine. It's not even feasible. But gradient descent provides an elegant, feasible, and very efficient alternative. And that even works better. So, by using a smaller data set here, you learned how to implement gradient descent. Next time when you deal with a real project with a real data set that is huge, remember that mini-batch gradient descent is there to solve your problem. Let's print the weights. Now we have the model trained, we got the weight matrix values for the output layer. I like to compare the values of the weight matrix with the values of the matrix trained without mini-batch gradient descent earlier. And I took a screenshot over here. We can directly compare the values. Because we started training the model with the same randomly generated weight matrix values, and those values are very close to 0. So generally, the more time that you train the model, the bigger in terms of the absolute value the weight matrices will be. And recall that we use the same number of epochs for this training as well as the training that I demonstrated before. So both demonstrations use the same number of epochs, but based on the design, I know that mini-batch gradient descent should be more efficient because of the stochastic gradient descent mechanism. So if you compare the values, it can be clearly seen that several of the values is larger than the corresponding weight value if the model was trained without using mini-batch gradient descent. It's quite clear this value, third row, first column, is greater. Fifth row, first column is greater. Almost all, but not all of them, almost all of the weight matrix values tend to be greater than the corresponding value of the previous demonstration without using mini-batch gradient descent. So this is the evidence based on a comparison of the implementation with and without the mini-batch gradient descent. I didn't change anything else. The only difference is the mini-batch gradient descent. This provides an evidence for the efficiency and effectiveness of mini-batch gradient descent. And finally, let's evaluate the model performance. We will print the cost and accuracy of the model on a training set. Accuracy has slightly dropped, but the amount of drop can almost be neglected. The current average cost value is 0.53, which is smaller than the average cost value of 0.56 when the model is trained using whole set gradient descent. So after the same number of epochs, current average cost value is further reduced. This is another evidence that mini-batch gradient descent really worked, even on a relatively small data set. Now let's plot the curves for the cost and accuracy. It's here that you can observe the greatest improvement of the learning process because of the mini-batch gradient descent. Let's run this. You see smooth lines. You no longer see the oscillations when the model is trained with whole set gradient descent like these. These are curves of cost and accuracy previously. To me, with gradient descent, looking at these curves gave me the greatest satisfaction. Mini-batch gradient descent is working. Finally, let's take a look at test set performance. Test set performance is 0.92, consistent with the training set accuracy, so the model is good. That's all for this video. In this video, I demonstrated how to understand the differences between whole set gradient descent and mini-batch gradient descent. I explained at a conceptual level what are the necessary changes to the implementation of the multi-layer perceptual model when you modify the implementation from the whole set gradient descent to mini-batch gradient descent. Then I showed you what are the necessary modifications to the codes, including initialization and the main codes, the outer loop and the inner loop, when you want to modify the codes to implement mini-batch gradient descent. Finally, I showed you the same learning curves of cost and accuracy, and you see very clearly that with the mini-batch gradient descent, the learning becomes much more stable and the learning is more efficient. After the same number of epochs, the average cost reduced, whereas the accuracy level remained consistent. I hope you have enjoyed this video. See you next time.